What we're going to attempt to look into is utilizing the variational principle, also called the variational method, and applying it to concepts from our nuclear magnetic resonance spectroscopy. Now, taking a step back, what we're actually looking into is ways of approximating solutions to the Schrodinger equation to get energies for various wave functions. One that's used best is perturbation theory, which is excellent for when an exact solution of the Schrodinger equation can be obtained, and that exact solution will be just slightly off from the real system that is being studied. Therefore, that exact solution will just need a little slight perturbation to best approximate the real solution. And this essentially is just taking our solvable system, which is psi naught, applying the Hamiltonian and getting an exact energy solution, which we can then take a slight perturbation, an additional energy to approximate a closely similar system or similar in energy to get psi. Now, the Schrodinger equation does not always have an exact solution, and we don't always have either easily solvable solutions or exact solutions that can just be slightly perturbed to get our real system. In that case, one of our options is the variational principle, which revolves around guessing a suitable ground state wave function, and if there are certain parameters that can be adjusted in that wave equation, adjusting them to help minimize our guess energy to more approximate our true ground state energy. The method of this is just simply making a reasonable guess on the wave function that is representing our real system, applying the Hamiltonian, and our guess wave function will in reality be a superposition of the various possible wave function solutions to our Hamiltonian, multiplied by their various normalization constants. Therefore, multiplying by the complex conjugate, we can obtain the energy back for our guess wave function. And this should be greater than or equal to the sum of all our various energy solutions of psi 1, 2, 3, so on and so forth, multiplied by their various normalization constants squared. Where this is valuable is that for every energy level above our ground state, what we know for sure is that those higher energies for E2, E3, so on and so forth, they will always be at least greater than or equal to our ground state energy. So one approximation is simply, for our long equation, just replacing E2, E3, so on and so forth with the value for our ground state energy, or just putting in the symbol E1, pulling that out as a constant, which will cause that to be multiplied by the sum of our normalization constants, which by definition should add up to 1. Therefore, the strength of the variational method, variational principle, is that our guess wave function will always result in a suitable guess wave function, will always result in a energy that should be at least greater than or equal to our actual ground state energy. And if we have a wave function where we can adjust certain parameters in our guess, even if that wave function is not the true wave function of our system, we can try to minimize those parameters in such a way to better approximate the actual ground state energy. Where this can be used for our nuclear magnetic resonance spectroscopy is instead of looking at typical electrons, we can instead look at the nuclear spin states for the nuclei of atoms or the atoms in a molecule, as well as looking at suitable allowable transitions in those spin states to eventually simulate NMR spectra. Now, the selection rule essentially is two parts. for nuclear magnetic resonance. First off, the allowed transitions are those where the magnetic quantum number changes by an integer value of 1. And additionally, for systems with multiple spins, only one spin may flip or change during an allowable transition. So that's a way of thinking. The spin for a proton that can be looked up as plus 1/2, minus 1/2, just like with an electron. So for single spin systems, an allowable spin change would be changing the magnetic spin from by +1 to -1, so 1/2 to -1/2, so on and so forth. For coupled systems, like for those of two, a system of 2 nuclei, well, then that would be the overall magnetic moment, which is the sum of the individual magnetic moments, and whatever those add up to, the change from one transition to another for the total, or delta capital M, should still be between plus or minus 1. So looking at a coupled 2-spin system of 2 nuclei, one way of looking at it is 4 possible states for those coupled nuclei, where they both spin up, both spin down, or opposites. And if we take the total magnetic moment, total magnetic spin, 1/2 plus 1/2 could be a total of 1. If they're different, that would add up to 0. If it's -1/2 plus -1/2, that would add up to -1. Therefore, the possible transitions for a delta capital M change in up or down by 1. It could be a transition between state 1 and 2, state 1 and 3, also state 2 and 4, and 3 and 4. Therefore, we have more than just the typical spin up 1/2 to spin down 1/2, and vice versa. For applying the variational principle to multiple nuclei, or for the nuclear spin states, here's a few steps from Chem Libre texts and their website, which is helpful for applying them. Step 1 is just choosing a spin wave function to try out, to put through the following steps to see if it does result in a spectrum that is close to a experimental spectrum. Next we'll be applying the spin Hamiltonian, taking into account the magnetic properties, parameterize, which is taking logical guesses and values for the expected chemical shifts and coupling constants between those various nuclei, and then evaluate the matrix elements for their secular determinant. Then going a step further to solve for energy eigenvalues and eigenfunctions, and then building a transition probability matrix that obeys the selection rules for NMR. Afterwards, you determining the allowable transitions and their intensities to generate a simulated NMR spectrum for that model nuclei or model multi-nuclei system.